A lot of students don't realize the importance of understanding this definition of limit. I'm telling you, if you want to be able to do your assignments or test, you have to understand this definition, especially if you're a math major. Before we try to understand the definition, let's first make sure we fully understand this limit expression. Let's first look at this function. What's f3? 2, because that's the y value at x equals 3. The upper dot is an empty dot. That's why it's not colored. Now, what's the limit of fx when x approaches 3 negative? 3 negative means it's approaching from the negative side. So from the left side, it's approaching 2. Then how about the limit of fx when x approaches 3 positive? 3 positive means it's coming from the positive side. So from the right side, it's approaching 5, right? Okay, so let's look at this function this time. What's g5? 3, obviously. And how about the limit of gx when x is approaching 5 negative? So it's from the left side, and it's approaching 3. And how about from the positive side? It's also approaching 3. When you have the same answer from both sides, you can combine the two expressions into one, such as x approaching 5. So in the left graph, the combined limit doesn't exist at x equals 3 because the two sides' limits are not the same. From here, we can conclude that if a function is continuous at somewhere, the limit should also exist at that place. Wait, so if it's a continuous function, then the limit exists? Does that mean if the limit exists, it's a continuous function? No, the reverse statement isn't true. We have this function as an example. What's f6? 6, right? So this line is like a stream of many dots, like this. And it's just one dot that got escaped from it and just hung up there. And there's our y value. Now, what's the limit when x approaches 6 negative? 4. Even if the point is not at 6, 4 and is up there hanging, the trend is still approaching 4, right? So it's approaching 4. Then how about the 6 positive? That is also approaching 4. Then that means the overall limit should also exist, and that should be 4 as well. So, limit isn't about the y values. It's about the trend. We don't necessarily need the y value at the destination for the limit. And look at the function. The function isn't continuous at 6, but there still is the limit at 6. So just because there is a limit, it may still not mean the function is continuous. Make sure you understand this, okay? By the way, this type of discontinuity is called removable discontinuity. Just an extra knowledge. Okay, now, let's look at the definition. The definition of limits is as follows. You've seen this definition from your textbook, right? It might not be the exact same statement as the one you saw from your textbook, but it should look very similar. In mathematics, people quite often define or theorize something that is so obvious. So obvious that you don't even understand why it's a theorem. For example, triangle inequality, which says that absolute value of x plus y should always be smaller than or equal to the absolute value of x plus absolute value of y. I mean, if you think about it, or just try to plug in any numbers, it's pretty an obvious statement. You might think, why is this even a theorem? It's the same situation in here. The statement may look a bit complicated to you, but I'm telling you, that one's also quite an obvious definition, so don't be scared. Allow me to explain now. By the way, the definition of limit can be divided into two definitions. Definition of left-hand limit and definition of right-hand limit. I just explained you about this x approaching from left and right concept, so this should kind of make sense to you roughly, right? Anyway, that's that for now. Let me first tell you this. This one is called, by me, a delta wall. And this one is called an epsilon wall. Yes, I literally mean walls. There are walls that are going to appear on a graph. I'll start explaining to you about this delta wall first, okay? Using these two divided definitions. So, we have a function on a graph. You see this inequality? This inequality means there's an x value in between c minus delta and c, right? So there's an x value moving around in between c minus delta and c. Make sense? And look at the other side's inequality. It says x is in between c and c plus delta. So that means there's an x value moving around in between c and c plus delta. So there you go, a delta wall. Now, going back to this left-hand limit, if I subtract all sides by c, it's gonna become this inequality, right? Then if I flip all the signs, I'll have to also flip the inequality sign. Then by just rewriting this, we'll get this. If we do the similar thing on the right-hand limit, so subtract all sides by c, we'll have this. And then, just for the future purpose, I'll just put a bracket. Now, if we bring those two inequalities together, you can see that we can combine them like this. So this is the delta wall from the original definition. And in fact, the original definition was the left-hand limit and right-hand limit definitions being combined. So, if you think about it, x minus c represents the space in between x and c, right? The gap. And it's just the delta wall is always wider than that space. That's what that inequality is telling us. It makes sense. Delta wall is built to confine both x and c. Now, the epsilon wall. You know, when we have a function, I just showed this as an example, that's the x value and that's the y value, right? Look at this. There's x in here, so this was about a horizontal wall. There's fx in here. What do you think this epsilon wall is about? It's about the y values. This epsilon wall is a vertical wall that's confining fx and L. Is everything clear so far? Let's also remember this. Walls have the target coordinate or target point c, L at their center. It's always like that, okay? And also, both sides of each wall should have an equal space, so equal width. Delta this way and delta this way, epsilon this way and epsilon this way. Equal width. Alright, finally, let's try to understand the full definition. We are back to our original definition. I'm gonna translate this for you. So, definition of limit by Remistad. Alright. This means the limit L exists, right? The limit L exists if, for any given epsilon wall, there always exists a delta wall that obeys this inequality, so can trap those x and c, and also satisfies this inequality at the same time. So, if this isn't true, then what should happen? The limit should not be L, the limit should not exist, DNE. That's what it is, alright? If that statement isn't true, the limit shouldn't be L. Alright, I'm gonna tell you something. Sometimes it's easier to understand mathematical theorems by wrong cases. I mean wrong examples. So let's think about a wrong case. Here, at C, the overall limit doesn't exist, right? We learned that, because the left and right hand limits are different. So let's see if the statement holds in this case. So this was the translated version by me. If for any given epsilon wall is at any given. So I'm just gonna draw an epsilon wall with a random size. And of course it should be centered at C. Okay, for any given epsilon wall, there always exists a delta wall that obeys that inequality. Okay, let's see if this delta wall works. X and C are both trapped inside, so that's good. And also satisfies fx minus L being smaller than epsilon at the same time. Let's see. This is our fx that can move around inside the delta to satisfy the first inequality. And fx minus L means the spacing between the two, right? Is that space wider than epsilon? No. Nice. So we do have a delta wall that makes this possible. Great. So the limit exists then? No, not so fast. You know why? Because at the beginning, I said for any epsilon wall. Any epsilon wall must work. We have only tried this one epsilon wall. Let me try this epsilon wall. So it's a bit narrower this time. So now let's see. Oh, this delta wall has a region where it allows fx minus L to become wider than epsilon. That's not good. But it's okay. We just gotta find another delta wall that can satisfy it. As long as there is a specific delta wall that can do that, we'll be fine. Let me try to reduce this delta and see if this can stop fx from escaping the epsilon region. Yeah, now fx minus L is never wider than epsilon wall. You see that? It can never become wider. Great! So there still is a delta wall that can satisfy both inequalities at the same time. I'm meaning having x and c inside the region and at the same time not allowing fx minus L to become wider than the epsilon. So can we now say that the statement is true and the limit exists? Nope. I said for any epsilon wall, we should be able to come up with a delta wall that can satisfy the inequality. Yes, I'm gonna keep trying to refuse this statement as much as possible. That's what the mathematician's mindset should be, you know? We have to be as picky as possible by trying to find a loophole. There. Now I've shrunk this epsilon wall even further. The statement says it must work no matter what size of epsilon wall is given. Now, let's see if there's any delta walls that can satisfy both inequalities. I mean, first inequality is always meant to be satisfied. The first inequality just means we're only talking about the x that's between the delta walls. But now the thing is, does fx minus L not get wider than epsilon? Oh, it's wider already. So let's come up with another delta wall that can satisfy it. Alright, let's play again. Oh no, fx escaped again. But now, how can we make fx go back inside epsilon? Is there any other delta wall that we can draw such that fx is inside the epsilon? Is there any delta walls that could do that? No, there's no such delta wall that can satisfy the second inequality at the same time. We just found a wrong case that can reject this definition. Therefore, the limit should not exist. And in fact, the overall limit of fx at c should be dne, since the left-hand limit and right-hand limit are not same. So, the limit L should not exist. Wait, but then what was that L until now? to tell you the truth, L could have been the upper point as well for the right-hand limit. So it didn't even make sense in the first place. But you know, even if we considered the upper dot, same thing would have happened anyway. So, you can immediately tell that this one should have the limit L. No matter how small we make the epsilon wall, there will always be a delta wall that can trap all of those x, c, fx, and L inside the epsilon wall. So this is the last slide. What was important in this definition? This one, for any given. So to have a limit, any epsilon wall must work. I wish you all the best and hope to see you again.